Okay, here's the very end of page 6. I started talking about number 13 and it got kind of complicated. All right, if I'm given, so I don't know which triangles it could be. It actually could even be, I mean, if you really want to get weird about this, it could be TOR and SOU. Those look pretty congruent, although it does ask me for overlapping. It might even be that TOS is congruent to UOR or something, but it doesn't really look like that's going to be possible. But from the beginning, you actually don't even know. Oh, wait, except for those aren't overlapping. But in proofs in general, I mean, there could be a lot of triangles in a figure like that could actually be congruent. The only overlapping ones that appear to be congruent here are one of those two. But from what we're given here, we're kind of steered in a certain direction, probably. If RTS is congruent to UST, and RS, that's this thing, is congruent to UT, I'm probably going to be looking at the top set, so probably this one and this one. Let's draw those separately. Let's get this, I'm going to move this aside for a second. If I move those around, the top triangle is, sorry, the top sort of triangle on that side looks like that, and this one is TSU. I can claim that one by reflexive. I was given the big angle at T and the big angle at S, and I was also given RS and TU. Well, guess what? This is side-side angle. Ain't no such thing as side-side angle. So these are none. Okay, so since that wasn't even true, and you're never going to want to look at this again, in terms of those markings, I'm going to go ahead and get rid of that. Let's talk number 14. On 14, they say there are two different pairs. Well, I guess the two pairs are probably going to be the ones I was looking at before, TUS and SRU, and TRU and SUR. Okay, why is that? Well, we have RT and US, we have TU, that whole thing, and SR. In both sets, the third missing side is reflexive. That's for the lower side of the big triangles, and this would be for the upper side and the two little triangles. So both of them would be true by SSS. Okay, great. Now, next page. Example 1, it asked me to prove it, like lots of these do. Okay, so what we're given, B is congruent to D, and those things are parallel. Great. CAD. Why is CAD congruent to AC? CAD. Why is CAD is this thing down here? Why is CAD congruent to ACB? Oh, because of those parallels. Those are AIA angles. Okay. AC is congruent to itself because of reflexive. That's not such a hard thing. Why did they do that, though? Well, to get congruent triangles. If I look at like what triangles are congruent here, it's not too hard to figure out that we're talking about the top triangle and the bottom triangle. A in the top triangle has no angles or anything marked, so that would be C in the bottom triangle. B in the top goes with D in the bottom, and the other point is A. That now is because what's marked here is angle, angle, side, and then, of course, this is always after the triangle congruent step. Example 2, O is congruent to P is congruent to 90. You can mark that. That makes them right triangles. That's what that's going to be good for. Now, whenever you see this R or is, and then there's a term, it's usually going to be definition of over here. And that's sort of leading me to think that maybe these are going to be congruent by HL, otherwise why bother with this? But I don't know yet. I'm getting ahead of myself. MN and QR, that little thing and that little thing. Oh, is this going to be one of those segment addition things? I hate that. Look, reflexive, I bet you $1. That's going to be that one. And then we're going to add RN. Yeah, I called it RN. They call it NR. We can add things to both sides. Oh, I forgot to say this. I forgot to say given. Getting ahead of myself on segment addition. Addition property of equality. MN plus NR is really MR. And QR plus NR is really NQ. They call it QN in the next step because of segment addition. Oh, here's how you know it's an annoying segment addition postulate problem, because that's already one of the given reasons. All right, so why is this one equal to this one? Well, because I already knew that was congruent to that. I called that transitive. You could call that substitution, and you'd be okay. And then, okay, so now I have this whole thing congruent to this whole thing. That's a side. Oh, I didn't mark this from the beginning. I was getting so far ahead of myself. That was given too. OMPQ. So in each right triangle, I have a hypotenuse and I have a leg. They told me it was a right triangle. That's really a big hint when they say. I mean, I said right triangles can be good for all that other stuff, like right triangles at the beginning. Just because they're right triangles doesn't mean it has to be HL. But when they put this is a right triangle in the middle of the thing, you know it's kind of steering you towards HL. Because if it was just going to be SAS or ASA, you wouldn't have to have listed the fact that it is a right triangle. That would be ASA without that. Okay, this is one of those put them in order reasons. This is going to come right before that. Whoa, what happened to the middle of my... Just a sec. That was weird. Okay, so what's given here is that stuff. Let's mark it. 1 is congruent to 2, and JAB, this big thing, is congruent to this big thing. Wow, it'd be really nice to draw these separately. You could do that, JAB and KBA, kind of like that, and I just marked 1 is congruent to 2, and the big anglet A and the big anglet B. Oh, and guess what? This stuff is reflexive with itself. Oh, yeah, that's what this stuff's about. I can do that right now. That's fine. That's enough to say angle side angle on these two triangles, and that sets me up for CPCTC. Okay, getting sick of that same rhythm there. Deja vu all over again. 1 is congruent to 2. Oh, not only that, they're right angles. Let's mark them accordingly. They are right angles, 1 and 2. KZ, woo, okay, that's weird. This thing here is congruent to YM, which is this whole thing here. All that stuff is given. Triangles are going to be congruent because of HL. Those go together, and then that comes last. What am I trying to prove? YZ. That's got to be last. Probably because it's going to be in that order. The triangles are going to be congruent first by HL. This will be what follows, and that the fact that they're right triangles is the only other step. I didn't even think about that proof. This is kind of a no-brainer the way this has to go together. Let's read through it first, straightforward, just to make sure. Given is that stuff, the right triangles. Yeah, when they say are right triangles, that's really very HL foreshadowing there. I didn't even get to the point where I marked this. PY is congruent to ZP. I didn't even do that. In each triangle, then, I have a hypotenuse and a leg. Yeah, that's true. So you have to say they're the right triangles. You have to then you can say they're congruent by HL because that's already given. Really, HL is given. It's just it looks a little bit weird because they're overlapping. All right, 5. Oh gosh, we have 3 proofs to do in this one thing. All right, so I'll do 5, and I will save room for the 2. I'll mark it up and then I'll erase it each time. And you can pause and rewind if you want to see the other ones. So the final version, this is going to just stay with 7 because that's the way it is. Okay, so the given stuff is given. And here that's BAD and C. BAD, that's a right angle. And BCD is a right angle. And AB is congruent to BC. Okay? Prove that triangle BAD is congruent to triangle BCD. Well, looking at those two triangles, BAD and BCD, they're right triangles. They share a hypotenuse right there. Let's go ahead and get that out of the way. BD is congruent to itself. Congruent to itself. And then I think I'm done. Right? I got a hypotenuse and a leg there. Done. Game over. Okay, look at that. I'm going to pause, or you can pause and rewind. I'm going to, I guess rewind and pause to see that graphic again. All right, given in 6, is that M is a midpoint? Well, I'm not even going to think about that. If M is a midpoint of AC, I don't want to forget what's going on here. That means AM is congruent to AC. This is how you spell because it's a midpoint. Okay. So, oh, and it's also the midpoint of BD. Same reason. Sorry, that's not A. Different segment now. B, the distance from B to M equals the distance from M to D. Great. Do I have congruent triangles yet? I'm trying to prove AB is congruent to CD. AB is CD. Oh, AB is in a triangle. I think I need to say another thing, though, but AB is in a triangle with M, like C and D are in a triangle with M, but I think I have to go this way to be careful. Because I have vertical angles here. Angle AMB is congruent to angle CMD. Those will be helpful because they finish up side angle side. And then I get what I needed here for AB. great. 7. Okay, I'm going to get rid of the markings. Come back and look at that if you want to look at 6 again. In 7, AB is perpendicular to CD, so that's a perpendicular. AD and DC. And AC is a bisector of BAD. All right, so before I even think about that, I'm going to say step 2, angle BAC is congruent to angle CAD because it's a bisector. Okay. And the given stuff is up there. I already marked it. Okay, I'm trying to prove down here that, it's just angle triangle, or triangle congruence. ABC is congruent to ADC. That's not bad. That's the top triangle and the bottom triangle, right? ABC, ADC. Oh, I've got a shared side here. Look at that. This thing's congruent to itself. That's helpful because now if you look at the two triangles, I have an angle and an angle on the side. Right triangles, not HL. I didn't have to say it was a right triangle, didn't matter. I just used the right angle as like any other angle. Okay, so the markings here are for 7 when I leave that as a saved version. All right, 4-6. All right, example here is x is the midpoint, and there's a plan for it. Let's do it down here. X is the midpoint of BD, so the definition of midpoint tells us that the segment from B to X, they have congruent, so I got to say it that way, is congruent to XD. Let's mark it. We also know that AC is perpendicular to BD. Great. If two lines are perpendicular, then they form adjacent angles. Which ones do I care about? There's 4 here. I don't know which ones they want me to list. Eventually, I'm going for triangle ABX and ADX. So let's do the ones that are in those triangles. Angle AXB is congruent to AXD is, I think, the one they want. Again, since I'm looking at those two triangles, here's a reflexive piece that would be useful. Those two triangles don't share anything else. So now in the two triangles, I have all this marked, so that's great. And whoa, sorry, wrong button. Oh man, just a second. Wow, I was just trying to scroll a little bit and it went everywhere. Okay, AB is congruent to AD for the same reason. AB and AD, okay, yeah, that. Oh yeah, this is CPCTC. This is the same reason that BAC, oh gosh, these little things right here. That's CPCTC. It's a long proof. That looks like it's because it's the same thing. We call that reflexive. AC, that's this whole thing here. Now what triangles do I have? Well, I just recently listed this side, this angle, and this side. Looks like it's probably side angle side. Yeah, I have a big side here of AC. So I'm guessing it's going to be triangle AC something and AC something else. Well, the only thing in this picture is ACB and ACD. So that's what we're looking at. And what do I have in ACB and ACD marked? I have a side and an angle on the side, and the angle is the angle between. Wow, we've used side angle side twice. That can happen. This is a 2-stager. We had some of those in homework. And then why are the angles congruent? A, B, C, this whole thing, and this whole thing. That's because of our old friend that always comes right after a set of congruent triangles. All right, so now same diagram, different proof. Let me copy. All right, the copy paste was just too difficult. I thought I'd just draw it here. Okay, got plenty of room. That's probably what you would have to do anyway. All right, what's given is x at the midpoint of BD. Okay, x at the midpoint of BD. So let's just go ahead and get this out of the way. That's going to help me say BX. And I would encourage you to do that. Don't even look at anything else. As soon as you see the word midpoint, just translate that into something useful. The only thing that it's useful for is use the definition of midpoint to say what parts of it are congruent. We also know that BC is congruent to DC. Okay, I'm trying to prove that angle BAC is congruent to angle DAC. BAC and DAC, which is these two things here. I'm not going to mark them yet because I don't know for sure. What do I know? Well, these angles, BAC and DAC, those are part of these big triangles. Looks like it's going to be another 2-stager because the stuff I know about over here in triangle BXC and DXC is not exactly helpful. Oh, why did I skip a step there? To leave a space for that. Bam! All right, now look at the bigger triangles. BAC and DAC are only triangles, parts of triangles BAC and DAC. I don't have enough marked on those. I have a side over here, a side over here. I have a big reflexive side here. Right there. I'm also trying to save time here, sorry. The CPCTC I forgot about. I also need to say, whoops, over here, angle BCA is congruent to angle DCA from the CPCTC. Now I have enough stuff in those two to say side angle side, and I'm done. Okay, by CPCTC, of course. All right, see you in the next part.